Hello, it's a great pleasure to be an industry partner with Ryerson University and to offer this presentation, which will include the planning of a construction project, drawings, details, and also the construction phase itself. Let's start. The content of the presentation will include the project planning, types of project drawings, what are the different types of the project drawings. If you have a structural steel building, how you can provide the drawings for that, and what will be the details on the site. We will go through some project pictures. And if you have concrete building, what will be the design drawings for this building, and we'll go through some construction details for that. And at the end, I will speak about the foundation and the soil condition. In the project planning, I put this chapter or this part in the presentation because I found that some of the students, they are really interested in knowing different stages of the project, not only in the structural design or in the civil engineering, but in general. That's why when you speak about the project planning, at the beginning, there will be an owner or investor who wants to build a project. And at the beginning, he can have a piece of land like that. And this piece of land, he has to choose it, and there will be in the city in general, if the city map like that, there will be some zones in the city. Each zone has some requirement or some restrictions. For example, if this land is in this zone here, then he has to abide by the zoning bylaw. And also there will be environmental approval. And after that, he has to choose the consultant. And if he has an industrial project, mainly he can go to the mechanical engineer and structural engineer, and then they can build together the building. However, in the most cases and the most of the buildings, they go to the architect, and at this point, the architect will check the zoning bylaw, and he will determine what he will do with the land. Now, if that's the land for your project, the architect cannot build the project through this land. There are some restrictions for the buildable area of this land. So what are the factors that affect the project? We will go through that in the next slide. The first thing is the budget. The owner or the investor, he has an amount of money he wants to use in the building of this project, and the architect will use a document or contract from OAA between him and the owner. And in this contract, the owner estimates the budget for the project. This budget is important for different reasons. Some of them is to have the idea about the project type, the material, the finishing, the expenses. And another thing also, the architect can charge the owner based on a percentage of the construction cost. So the budget of the project has a big impact on the project itself. Now, the other thing is the location. As I mentioned, if you have a project in a residential area, you can't have an industry building within it. Or if you have in a land in an industrial area, you are not allowed to have residential area in this land. So the location will have a big impact on your project. It can also have an impact if you have your project on the lakeshore, if you have your project in far from the city and you can't provide concrete for this building. Like, it's very hard to get concrete from concrete mix. So that in this case, you might go with timber structure or steel structure. So the location of the project has big impact on your building. The material, what are the available material which can be used in the project, and at the end, the type of the project. So for example, if you have an airport, normally airport with a big span are made of steel structure. I saw only two airports from concrete and they were not beautiful. So most of the time, if you have airport, so that will be steel. If you have a sport hall, that will be steel. Other buildings can be concrete or timber. So the type of the project has a big impact. Now the location of the building, as I mentioned, there are some restrictions for the buildable area and also the height of the project itself and the use of this area and so on. If you look at this table here, it's from one of the areas here in Ontario, and it gives you the, if you have a land for the detached dwelling, the minimum area which you can have is 557.5 meters square. So if you have this area, so you can think about detached dwelling or semi-detached. Semi-detached, you will need more than, you will need 743. Now, one thing what they say here is the maximum lot coverage area, which means what? So if I see here, if I draw here, let me draw that, get a pen, and if I draw here this land, which now is at the top, now this area here, that's what can be built in this slot, which is 35%. So 35% of the whole area. That's very important. And the other thing is the front yard. Like here, A, he has to go back here with 7.5 meters, B, and so on. So there are some restrictions. And the other one here is the maximum height. If I go here and say the maximum height, you have this cross section, and that's the land and the top of the roof, the highest point of the roof, then you will have this height of the building, that's the total height. So this height cannot exceed 12 meter in this area. So based on this information, if we say that the architect had already made his mind and he starts now with having an elevation with a building like this, that's an elevation, and he wants to have the plan, and with this plan he wants to go to the structure engineer to build his building, some walls and doors and so on. So if he has something like this and he wants to have to build his building, so what will be the different stages which he can use, or what type of drawings he can we expect in this case? So let's go to the second slide, which shows us the type of the project drawings. So you can have design drawings or you can have something called shop drawings. So the design drawing will have the goal to present the member design, size, configuration, connection, types, elevation, and so on. So you will have design drawing, which we use normally in the at the university or in the offices. This drawing won't come at one stage, and that also is not required from you neither in the office or in the capstone project. We do these drawings, or we create these drawings on stages. So the stages of the design drawing, the first one is schematic design. With the schematic design, we know where to put our columns, what is the system, and we have some idea about our drawing, our design, and the load path. After that, when we agree on some column locations, material, and so on, we start with the second stage, which is the design development. We move forward with our design, and that's the development of our design. And after a specific time or percentage of this design, we can say these drawings now are ready to go to the city, which means that we have enough information to satisfy the city requirement. And when we apply to the city, then here we wait some time to get the approval of the city, or sometimes they have questions. Now, in this case, we are working on the tender drawing. So we have the drawings with a specific accuracy, good enough for this city, and we create more details here for this drawing. And this drawing will be used for the tender. And the tendering process will need about maybe 8 weeks. It depends on the size of the project. So you wanted to get the project for tender, and we still not 100% complete with our drawing. So we are still designing or moving forward with our design. So at this stage, we can issue a construction drawing, and the construction drawings will have the abbreviation of CD. And some of the offices, they say we are 100%, we go with 100% CD. And realistically, there is no 100%. So some offices, they use 99% CD, because we expect some items are really missed, or by mistake, or any typing mistake. So we can't say 100% CD. We can say most of the time 99% CD. So it's an office policy. But this drawing here, it's what will go out for the construction process. Until we issue or this drawing is ready, so we should have get or received the permit drawing, and the contractor will submit to us, or to the project manager, his price. So the owner will have the best price from the contractor, and he has the final design drawing. Now somebody can say, but you know what? The construction drawing might change something from the tender drawing. Now we discovered something, and we modified the drawing, and so it's not the same drawing as what the contractor put his price on. And that's true, and it happened. So the contractor will have some adjustment, and we have to be fair, and that's very important to be fair in the construction industry. And if you save in the amount of material, you have to discuss that. If you use more material than the tender drawing, then you have to disclose that, and we discuss the impact of these changes on the project cost. Now that here is the design drawing. Now after we finish with this design drawing, and the contractor takes the drawings, and he creates something called shop drawing. Shop drawing is like they start to manufacture some items in the shop, and they try to bring many items as ready as possible to the site. So to create something in the shop, they create shop drawings, and they send it to the consultant for approval. So the shop drawing, they prepare the member in the shop and minimize the work on the construction site. That's the goal of it. Now, how they create that? When they read the structure drawing, and then they started to know for example, if you have here two beams, and you have another secondary beam here, and you know the distance from these beams, between the beams is 8 meters, 8,000. And now this size here, after they calculate the wedge, the flange of the steel, and the other flange, and then they can say this member here will have this shape. They cut the flange, and you have the web, and then you can have this shape of your steel beam, right? So that's the flange, and that's the lower flange, and they have to cut the top flange because of the interference. Now this length here, for example, might be 7990, for example, that they calculate that. So they submit to us or to the consultant this drawing and say, okay, here we have few how many holes or for the bolts, and that's the cut, and that will be our beam. This beam drawing will be submitted to the consultant for approval, and when it is reviewed by the design team, then we might say, you know what, there will be here an opening and you have to add that in the site on the shop. So you need to add an opening, to create an opening, because there is a pipe going through this. So we add our comments on the drawings and give it back to the contractor. So we have correction, and then we ask for resubmission, to resubmit the drawing. And when we approve it, we said done, approved, then they can start the manufacturing process. So they start to prepare that, and when they send it to the beam to the site, it will be in this shape. Now I will speak about the steel design drawing. If you have a structural steel building and how the drawing will look like. So if you see here, it's a plan of a big project, and it's a little bit challenging to see here. I will take part of that and we will discuss it. But here on this side, you can have some symbols which I would like to go through them to explain some of the meaning of it. Like here, column below, if you have that's elevations, and in this elevations, for example, you have the column is here, like let's have 3 columns, and here the other column will be like that, stops here, and in this area the architect wants to have a big space, so he can't have a column here, but the column will be moved to the other side. Okay, so in this area, when you have the plan here, you can show this column and say that's a column below. Okay, the column doesn't go up, the column is here below this level. And when you look at this drawing here, the column starts from here going up, so that means here you have column above, for example, and this means this here will be a transfer. So you can have something called column above, column below, and you can have top of steel, and unless noted otherwise. So you have to go through this notes, which will be at the beginning of the general notes, at the beginning of the project. And here, if you go to the second drawings, that's a big area or another area of the project. And if you go here, for example, you have this here as the beam size is W410 times 67, and here you have something called 40, and 40 is number of steel studs. I will speak about that soon. And here you have C equal 25, and C is abbreviation of the camber, and the camber is when you have the beam straight like this, and after you apply the load on the beam starts to deflect, and this deflection can be reduced by having an upward camber. So you ask the manufacturer to bring you a beam with upward deflection to reduce the total deflection of the beam. So instead of getting a deeper beam because the deflection criteria is not satisfied, so then you can get a beam with an upward camber, and when you apply the dead load on this beam, it will be straight. So you can have some camber in this beam, as we can see here. You have a camber of 25 millimeter, and when you apply the dead load, it will be straight, and then the additional deflection will be from the live load. It will be straight almost, like you can't have it 100%, but there are some criteria how to specify the camber. Now we will speak about the steel deck. So it's 75 millimeter concrete slab on 75 composite steel deck. So the direction is here, which means you see the direction here, this one and this here. So which means that the here the steel deck, it looks like that. That's corrugated sheets. Let me draw it. So it is here, it is corrugated sheet is going like that, and then that's the sheet itself, and this here is 75 millimeter, this depth is 75 millimeter, and then at the top of this steel deck you have concrete topping, and this is the concrete topping here. So this concrete is the 75 millimeter measured from here to here. That will be 75 millimeter on 76 or 75 steel deck. Okay, so now that's the direction of the steel deck, and here is the topping of the concrete. So we know the reaction, we know the beam, we know the camber, we know here is the number of steel studs, which I will speak about that. The steel studs is here, as you can see. The steel studs are here, and so that can create the composite action between the steel beam and the concrete at the top. So if you have a steel beam like that, and you can see the connection here, and then you can have the concrete floor, if you provide a formwork here, and then you can provide the steel reinforcement, and your slab in this case will be one-way concrete slab supported on these two beams, and then you can have your main reinforcement in this direction, and then in the perpendicular direction is the minimum reinforcement. So that's here is the way of having concrete slab on steel beam with composite studs here, with steel studs. Now, if you have a composite steel deck, you can see here, this composite steel deck with this profile will sit on the beams, and then you don't need a formwork, and that will be the formwork, and when you pour the concrete on it, so you will have a composite action, and that's very beneficial to reduce the formwork, and also it will have less reinforcement. I like this system to use the composite steel deck. It's very beneficial. Now let's go and see the video of installing these steel studs. So in this video you will see how they install or weld the steel studs to the, or shear studs to the steel beams. This gun. So the shear studs here, what provides the composite action between the steel beams, that's the top flange of the steel beam, and here are the shear studs, Nelson shear studs most of the time, and here you can have the concrete, and then you can create a composite action between the steel and the concrete. Now we know what the shear studs are and the composite steel deck, and we saw how they installed the shear studs on the top flange of the steel beam. Let's go to see what are the shop drawing for this project can be. For example, if you have this beam and you have here an opening, so you need to get some dimensions of the opening, and so they have to give us shop drawing. Let's look at the shop drawings and see how they look like. So here is a sample of the shop drawings which has been provided to my office, and also the shear studs. That was one of our projects which we did for the city of Toronto. So here you can see the beam, and you have this depth of the beam with the size, the total dimensions, and here the connection details. And now our comments here were to be to be 700 millimeter in the concrete, and here to be coordinated, and we need the drawing to be designed and stamped by a professional engineer. So we rejected this drawing because there is no stamp on the drawing, so it's not acceptable. But when you have a engineering draw or shop drawing, to make sure that it is right, it is like all the aspects have been considered, so you need to know that this drawing have been created and prepared by structural engineer. So there should be stamp on the drawing, something like this, our engineering stamp, right? You know that. So you will get it soon. So you will have engineering stamp. So with Beng, now you can start looking at you as this drawing. Without this drawing, without this stamp, so you can't accept the drawing. So my advice is, if you don't have the engineering stamp on it, so don't lose your time, because you don't know if when the contractor will bring an engineer, so which change he will do by himself. Okay. So the other one is another shape of the structure drawing of the shop drawing, and here they showed us some holes where they need to provide connection to another secondary beams or another connectors. So that's how they show the shop drawing. And here you have a web stiffener at the end of the beam to resist the shear, and here's the depth of the anchor rod. So that's how it looks like with some shear drawings, shop drawings. Now, if you have a steel structure, and what will be the details for that? Let's look at some columns details and base plate, and also we can see the steel beams and concrete walls. So if you have on the let me draw something here. So if you have the column like this, and then you have a base plate, it shouldn't be like that. So if you have a base plate, and so let's get a column, and here is a base plate, and this base plate, normally you have an anchor rod, and here an anchor rod, and that's a concrete surface. And we said that here we'll get grout to make sure that you have a full you have the a full contact between the base plate and the concrete surface. So how you can construct or put the anchor rods, that's here you have a schablon or have a template, and then you can put your anchor rods inside your formwork or your concrete member, and you have enough length from the top. That's very important. Okay, enough length to make sure that you have the grout, the top measured from here, sorry, that's the length what you need for the grout base plate, and here you will have a bolt, so you need enough length at the top, and then you can put your anchor rod in place like that. And here you can see in this foundation you have another dowels for the concrete columns. Now if we move forward here, you can see from this picture, that's one of the biggest projects I worked on actually. It's a very huge from the area, from the footprint point of view, and it's very big construction company. So you can see here, as I had my site visit, you can see here in many location you can see that an anchor rod was missing because they didn't protect it. When you have the anchor rods in place here, you want to protect that afterwards. You ask the contractor to protect it, because when they lose that, they have to drill another one, which is not, it doesn't have the same efficiency as the original one. And if you have an uplifting, so you need to have a design for that. You can use healthy, some healthy members, but it's not as perfect as good as this here. So you want to make sure that they protect the anchor rods in their foundation with something like that. You can see the anchor rods are here, and I can take here. You can see that here anchor rods inside, and they protected within with this box to make sure that it will be maintained. And here, if you have a steel beam, so we know that from the steel beam is here is the steel beam will be the steel column is straight. So the point when you deliver the steel column to the side, it should be as long as possible. So you can have 3 floors height or 4 floors, and it's normally you can have like 50 feet. Okay, so you can have more than 12 meters or 14 meters high steel beam, and then at each floor you can have a gusset plate and the connection to that. And here, if you as you can see, the steel column is straight, and in here you have a small corbel or bracket, and that's here an open web steel joist or a girder, and then you can have the girder connected to the steel column. The question is now how to connect a steel beam to concrete wall. So if you have a steel beam to steel column, you have a gusset plate. If you have a steel beam to another steel beam, as you saw before from the previous pictures here, you can have that steel beam to steel beam. There is nothing, that's very normal. But the point is what we can do if you have a steel beam connected to concrete wall. What can you do? So one thing is the cast-in plate. So if you have this here, let me use a marker here or highlighter. So if you have here this concrete wall, that's your concrete wall, and now you can have this here as your cast-in plate. So this steel plate will have this thickness, and this plate will have a studs to the back, and then you can put the steel plate in the formwork, and then when you remove the formwork, then you can connect it to the steel beam. Okay, let me make it simple and let's see that. So the steel cast in plate, that's a plate with the studs that will be prepared in this shape, and then they put it in the formwork like that, and then when it's finished it looks like that. So that was one of our project in Can Consulting. So you can have the steel plate cast in plate like that, then you can weld a plate to it, and then you can a gusset plate, and then you can have your steel beam connected to the steel here. So that's one of the options. So it has some limitation based on how much force do you have to resist and to connect here, and in sometimes you can create a bracket, and this here is your bracket here. That's here's the top of the wall like that, and the wall goes again like that, and here this space you can have your steel beam, and so from the wall you should have the anchor rods, and that will be sticking up, and then you have to be careful here in this edge because you have here in not too much space for the anchor rods. Okay, so that you can have a pocket. You can have a pocket in the concrete wall. Now let's talk about the concrete building. You can have cast in place concrete, and you can have precast concrete. So the cast in place, that's clear. So you pour the concrete on the site, and that can be used for the foundation, columns, walls, and beams and slabs. The precast can be casted on the site, on the shop, not on the site, on the shop, and then they ship it to the site, and then they assemble it on the site. So the pre-stressed concrete, so they can apply tendons and stress the tendon, and then they pour the concrete at the top of that, and then you have it as pre-stressed concrete. In the post tension, you can have conduits within the concrete and pour the concrete slabs or beams, and then when it's hardened enough, then you can apply some stresses in the tendons, and that will be post tensioned. Now for the regular building, you can have here in this picture, you can have the basement floor, and then you can have, that's here, the first floor, second floor, you can have the roof, and that's number 2 is this first floor, and that's the basement, and then you can have number 4 is the slab on grade, which is the basement, but here number 1 it shows the space in general, not on the is not pointing at the slab itself. You can have here flat slab, which is number 5, and flat slab you can see here that has a drop panel on, you can have column capital, and here you can have number 6, you don't have any drop panel or column capital, so that's why we call it flat plate, and this here is flat slab, and you can have the upturned beam at the edge here, which helps also to be as a parapet for the building. Now, creating a drawing for the concrete structure for the floor slab, as you can see here, you have this here are the columns, and now you have a thickness of the slab is 250, and here is 300, and you have a transfer here with 700. So that's the thickness of the slab, and here you can have the top of the slab. Here the thickness increases in this part, and then the other part has a recess in the level. So, and here you can see the steel bars. In a bigger picture here, you can see that this top bar here, you have 18 number 25 top, so it's 18 bar from here to here in this width, and that's number 25, and that's at the top layer. And this bar here, which is the top bar also, is 20 at 200 top. So here is it shows you there are some flexibility in the designation of your reinforcing bars. You can have the spacing, so number 20 is a diameter at 200 millimeter top, or you can have the number of bars and the diameter top within a specific distance or range. And here you can see that's 250 is the thickness of the slab, and you have a drop panel here, like a thicker, not drop panel, it's a thicker slab, 700, and here you have another 300 from the other side. So that's here is the shear wall number 10, and that's here stairs open, you have elevator, and you have here a beam and the grid line. So it's really that's the recess in this part. So you have to know this bar here, you look at there is also a dot and then the arrow, so that means this here, this beam, this bar will be distributed from this edge to this edge. Now there is another way of distributing the bars in the drawings. So as you can see here, you have different part. That's here is the top bar, and the top bar is dotted line, and then you have another top bar with overlapping length, and here you have the dot, and that shows you this top bar will go from this part to this side, from this side to this side, okay, and this bar here has the dot, and it will go from here to here. So the top bars here can be dotted, and the lower bars, as you see, they are solid bars. Okay, so you can have in your drawing for your project, you can have a special designation for the top bars, dotted bars. That's what we do in our office. And for the bottom bars, it will be solid. But always you have to get the point here on this bar and then the arrow. So that says this bar will be extended from here to here. So that's another way of showing the reinforcing in the concrete. And here you see that T equal 900. That means the thickness of this foundation is 900 millimeter. Now, after you create that, as you saw, that's the design drawing. Now we are talking about the shop drawing. Shop drawing in the concrete structure means that sometimes they send us some notes about the formwork, and most of the time it should be always the rebars, but it can have some additional to it. But mainly that's the main part, is reviewing the rebars. So the rebars here, you can see this height from this level to this level has to be corrected, and the overlapping length is something you have to consider. So if you have here steel bar goes from one level to the other and stops here, so you should, and that's a slab, you should have an overlapping length, and here you can have the new bar like that. This overlapping length depends on the concrete strength and the size of the steel bar. So that's very important. Sometimes they make mistakes with that, and there are different types of that. If this bar, the member is always under compression, or it can be under tension. So if you have a tensile force, then you will need a longer overlapping length. And so one of the other items which they miss on their drawings is that the number of bars. So if you can say here, I have the bars at 200 millimeter on center, 200 millimeter, and you have 4 meters. So if you say 4 meters, and so each meter will have 5, so it will be 20 bars. They can give you 20 bars, but that's not correct. That's it should be 20 spacing, and 20 spacing will mean that 21 bar. So if we say that here, this here is 400, 200 and 200, so 400, but the 400 spacing, so 2 times 200, but 3 bars. So the number of bars is always one more. So they miss in the construction industry, they miss sometimes 1 bar by mistake, sometimes, and sometimes also the overlapping length is not clear for them. Now, if you see some details on the site, so you can look at the foundation wall. That was one of our projects in 2016. So it's a foundation wall, and then you can see 2 layers of steel bars. We know that in the walls you are allowed to have only 1 layer of steel bars if the thickness of the concrete wall is less than 210 millimeter. So you can have 1 layer. So if it's 210 and more, so then you should have 2 layers. So you can see here that they have already 2 layers of reinforcing bars and 2 layers of horizontal reinforcement. Now at the top you need to add a top bar, that's important, and the bar splice, you can see here the bar splice, see that, and here. So the bar splice, when you have that, you try to have the bar splice staggered, that you can catch that on the shop drawing. For example, if you have 1 layer like that and you need to have a splice, and the other layer, then get the splice here. So don't get the splice in the same location. So you want to try to have them spliced that can prevent any cracks. It's recommended. So if you look at the foundation, from the foundation point of view, as a surface you can have deep foundation and shallow foundation. The shallow foundation is what you just saw in the in the shallow foundation. Will be just a spread footing and combined footing, or raft. Deep foundation means piles. So here, for example, if you can see here, you have piles and or caissons, and that will be the deep foundation. And this picture here is, I worked in this project, and you can see that it's 4 level basement. It's very huge building, and it had everything. That's the base is on a raft, and here the rafts are on caisson or concrete piles. Now, to have the soil report, like here, the soil report can specify the type of the foundation. So when you have the soil report, so you will have something like that. You will have a map, and you will have testing holes, and you can have bore holes, and they give you the total map of the project. And here uh, in the bore logs, you can say, or you can see the depth of each layer, and the layer category. So that can be silt, it can be clay, and the thickness or the depth of that, and if you have groundwater and groundwater level. So it gives you a lot of valuable information, and also the bearing capacity and the soil class for the seismic design. And here, to know if there is groundwater or not, so you have to look at the soil report, and then the long-term lowest ground level at this site is associated with the interference of the brown-gray silty clay soils. So approximately they say from between 3.8 to 4.55 meter below existing grade. So the groundwater level is located, it appears that the long-term groundwater level is at this location. So if you have a foundation and it is below this level, then you have to consider that. How to consider that? You have to look at the dewatering. Dewatering is to get a pump, and then you can have a hose and get this water out of your site. That's very important, and that's very important for the contractor, because that's additional cost, and also for his planning and his schedule. So that's very important item. Now you can see that this project, what I just mentioned, and here around it, it's a high-rise building. It's very important part of the city. And here, that year is 2007. So it's 13 years old now, this picture, and I'm expecting that there are many high-rise buildings here. So you can have concrete piles, you can have H piles. H piles, the H piles are really just steel piles, and they look like this. So they are steel piles. However, they call it H piles. So H piles and helical piles and micro piles, they are small piles. Helical piles, they are in helical shape. So now, what is that here? Why this level is not the same level as the other one? It's here the elevator bit. When you reach to the, like in the elevator, when the elevator stops at the basement level or the lowest level, then he has to have another space underneath the elevator, which we call it elevator bed. That's why they have this part here. Now, if you have pile caps with like H pile with pile caps, so you can have a drawing like that. Like here, you can have the 4 piles, and then the column is above that. You can have different piles underneath the shear walls, so it can be rectangular. So most of the time, it is, you are going to avoid combining footing together. So here you have to put the orientation of your pile cap to avoid interfering with that. So if I rotate this to this direction, I might have interference, and that's That's not preferred. We have to avoid that. So after we finalize the design of the foundation, now we can look at the foundation work itself. They start the excavation on the site, and then you can see if they need a formwork or shoring or supporting of the excavation or not. In this project here, that's the soil is cohesive, so you don't need any support to the soil. And here, after you get the strip footing, you put your formwork. And now there is a question, and we faced it. Sometimes you can pour the concrete against the soil. Is that allowed or not? It is allowed, but the only change here is when you pour the concrete against the soil is you want to have 75 millimeter concrete cover. So you want to change the cover and the thickness. And if you change the cover, that means your reinforcing bar will be closer to each other. That means your internal lever arm is closer. So the capacity or the resisting moment can change. So it's in the foundation in general. You can look at the impact of this change, but we can pour the concrete against the soil. Now, after they pour that and create the steel, they so you can pour the concrete against the soil, but change the concrete cover to be 75 millimeter. And now you have the formwork, and then you have the steel bars inside, and then you as a structural engineer, you want to go and inspect the site, so you can measure the spacing, you can see the bar diameter, and so on. And sometimes here you can, when you take a picture, and then you can have your foot in it. That's what I do. I put my foot inside the picture, so I can measure, or I can relate to the distance based on my shoe size. So I know some engineers sometimes they have the picture and they look at the brick veneer or concrete blocks, and they can relate to the distance based on the concrete blocks on site or the brick. So there are different ways of checking the site, but you will have your own way of checking that and recording your finding on the site, and you have to keep record of that for yourself. Now, when everything is right, inspected, then they can pour the concrete, and when they pour the concrete, you have to get the test, and that's true. We carry out concrete testing on site. What are the testing which we carry on site? You can check the delivery time of the concrete truck. You make sure that the time is not longer than what's required. And most of the time, we specify 2 hours for concrete transport, or 2.5 hours sometimes, but most of the time 2 hours. Okay, so 2 hours for to transport the concrete from the batch plant to the site. So if there is anything more than what the transportation time, then you can reject and send the truck back. So that's one thing. So the delivery time and mixing time, so that's very important to check. And after that, the temperature of the concrete. The third one is you take samples. Here it's not you, but there should be an inspection agency. They take sample and they have the slump test, as you can see here. And there is also the air content. You can see this part here will be used to have the air content for the concrete. So the air content is very important because if resisting the freezing and thawing. So when you want to have some space, some air inside the concrete to resist the frost, so air content is important item. So we specify the air content on our drawing. So we specify the air content. So air content, slump test, temperature, and the delivery time. Having said that, you have to keep record of your site report and with any changes in your drawing, and we want to make sure that we are doing our work on time, and also we want to be fair to our client and contractor and everybody. Fairness is very important in everything. So at this point, I would like to thank you for watching this presentation. And if you have any question, you can send me an email. Thanks for watching.